Hi, John.
Hey,
Yeah, I think it's probably a good time to start now. The
sure.
people who miss out will have to catch the stream on YouTube eventually.
Yeah, no worries.
Thank you very much.
Sure. Okay. Oh, we're recording already. Oops.
Sorry.
No,
Hi.
no, that's quite all right. Good morning, good afternoon. It's that's not what I want to do. Look at that. That's funny. Start at the beginning. I'm
Well,
going to.
thank you for coming today, and yeah, you can start.
Yeah, no problem. Let me camera off now. Okay. Started. See, obviously, I was thinking we're not already recording. So, well, good afternoon for you. Good morning for me. I'm coming to you from a cold Canada, but I appreciate the warm welcome. I do have some UK heritage myself. My mother was born in Stoke-on-Trent, and I hope to get there someday. Thank you, University, in particular from Idris, who we met at the UK GSUK conference and had a good conversation. Um, Feel free to post questions in the chat, or maybe we'll probably have time at the end. If not, my contact information here. If you have any questions, to send emails. Again, for many of you watching this recording, so it could be any time. Okay, let's get going. Let's talk about computers and performance.
Sorry, John.
Yeah.
Just to double check, are you sharing your screen?
Oh my goodness. Am I not? Because I'm not,
I don't
right?
think you are yet.
I didn't. You're quite right, as usual. There we are.
No, you are, yeah. I see
Oh,
your
I am.
contact details now, yeah.
Okay. Sorry about that. That's gracious. Too many screens. I've got too many screens here. Okay. Yeah, as I mentioned, my info's there. If you have any questions, feel free to send it across. Right. So now I can advance. Hopefully that's working good. Let's talk about computers and performance. All computers not created equal. So firstly, as a level set that I'm sure most of you know, uh, everything runs on a machine. Um, we talk about cloud all the time because we do lots of things in the cloud, right? Well, cloud, it's not a platform; it's a delivery channel. Now, I'm not criticizing that delivery system. I'm just pointing out that everything we do online is actually running on a physical machine somewhere. So for many like simple apps, we don't care what kind of hardware it runs on, and we don't know and we don't care, and that's fine. We accept occasional imperfections because it's free or it's least cheap, and we got to reboot. We just reboot. We don't really worry about why. It's not something that's really that terrible to deal with. Like most of us, I happily use my commodity PC to check email and surf online and play video games. Um, Now, different from that, though, systems that support the global economy, which is what mainframes are, those require higher standards. So a wise man named Bob Rogers, if you may have had the pleasure, he does occasionally come to the GSUK conference. He's a retired IBMer. I'm paraphrasing a bit here, the way he used to describe it. He would say, if Apple or Microsoft systems failed globally, it would be on the cover of every news site. He used to say actual newspaper. Of course, those aren't so popular anymore. And it would be expensive and it would cause massive global inconvenience. But if the world's mainframes failed globally, consider there's a over $20 trillion in daily financial transactions that would not be processed. Everything from just when we tap our card to buy coffee to making sure mortgages get paid and international transfers take place. These are all backed by mainframe computers. If people can't access their money held by a bank, if you go to the bank and say, that's it, I've had enough, I don't trust you guys, I want to withdraw all my money. If you can't do that, In most countries, that's illegal. The bank would be held responsible, and if this were to really happen globally in such a terrible event, the global economy would likely collapse. And I know this sounds very doom-ish, but suffice to say that would be somewhat more inconvenient than me being unable to play my video games. So we depend on these machines. So what makes the mainframe unique? Well, it starts with a proprietary and purpose-built machine with decades of engineering that's constantly enhanced. Most of you will know the original IBM System 360. That was so revolutionary at the time, specifically because every large computer prior to that, whether it was IBM or others that manufactured it, it had a custom operating system, custom applications to go with the custom hardware. So when they made a new machine, they had to make new operating system, new applications every single time. And IBM had the novel idea that, at the time, today we take this for granted, but then it was brand new, that we're going to make a machine that runs an operating system at that time called System 360, where when we make a new machine and I upgrade the machine, you can still run the same operating system. You can still run the same applications. You don't have to rebuild them all, which now we take that for granted, right? If you upgrade, whether you upgrade your laptop or whether you upgrade your mainframe, you assume that you can still run the same things. We call that backwards compatibility, which is the point at the bottom of the list here, and that's critical. So IBM solely designs, produces, and markets this marvelous Z machine and ZOS, the operating system, and the core subsystems. Now, what that does, because we make all of these things, we collaborate. This enables what I would call a truly integrated stack. So new transaction functions that are put into the subsystems are integrated with database functions. They're supported by ZOS operating system enhancements, right down to new instructions we put in the silicon chips. In other words, our teams talk to each other and they collaborate to design and build an efficient, integrated system. It's not just a really fast machine or a really, cool transaction subsystem like HIX or IMS or database like DB2. It's collectively, because they're designed and developed together, because they interact with each other in a very efficient way. That's what makes it so have all these qualities. This is this scalable, available system. So like take Intel, for example, huge company, they make chips as well, but they don't design their chips solely for Microsoft Windows. They, you might want to use it for all kinds of different things. And Oracle, which is a massive database company, among other things, they don't design their database to run on a specific type of hardware. They have to make their products generic enough to work with commodity parts. So that's a very flexible approach, but it's not going to be as efficient. Now, again, there's a market for commodity designs, and when your business needs to support thousands of transactions per second with sub-millisecond response times, zero downtime, and world-class security, you need a specialized system. And again, that backwards compatibility. Consider, not just the convenience of being able to run the same apps on your phone or your laptop. IBM's clients, some of the largest companies in the world, they invest billions of dollars and years of effort to design and deploy their critical applications. They expect them to keep running when they upgrade. They shouldn't be forced to change those applications, or even worse, rewrite them completely just because we've come out with a new machine. Occasionally that happens in other platforms. Sorry, I used to play DOS games. Now we have a nice little compatible DOS box that helps, but I digress. It's really quite an unparalleled marvel when you think about this. I'm not aware of any other system that does this. A Z17 today can efficiently run a program that was compiled 50 years ago, 50, as well as one that was compiled yesterday. I don't know any other platform that can do that. And the programs will run well. So again, just the result of this specialized integrated design results in a very, very efficient system. It's not, I think, hyperbole to argue that the mainframe supports the global economy. So this is interesting. You know, there's lots of talk, of course, of AI these days, and even that can be in and of itself a very interesting subject, because people will begin with saying, well, what's your definition of AI? And people will have different kind of subjective views of what that is. It's all just code, but you know, probably more advanced code is a fair way to put it. And I'm not going to get too deep into that, but just consider this. Imagine a system that didn't just track response times. It actually knew the response times that each unique application needed to achieve for your business. And this could be different for every business. And imagine that system also had awareness of the relative business importance of all of the workloads, hosting dozens or hundreds of workloads. So if the system got too busy, it could automatically adjust priorities and automatically divert limited resources to the most critical business sensitive applications. Now imagine that system could support and track thousands of transactions per second and make these adjustments every 10 seconds. In 1981, a visionary named Bernie Pierce, IBMer, he wrote a paper entitled An Automated Workload Manager for MVS. Now, his vision was ahead of technology at the time, but by the 1990s, it was reality. Bernie's vision was, rather than administrators setting static and complex dispatching priorities for all your workloads, these administrators, in collaboration with the business, would provide the goals. What response time do you need for this app? And the relative business importance, which is how critical is it that this goal be achieved relative to the other apps that are sharing resources. And you do this for each workload. And then you just let the system handle it. Let the system dynamically adjust the provisioning of resources, computing resources, processor, memory, you name it, to achieve these goals. Now, what I've just described for you, as some of you may know, of course, is the ZOS Workload Manager. And that has been a core part of the MVS, now ZOS operating system, ever since. So thank you, Bernie. Okay, let's talk about some of the roles in the mainframe space. Some of you might already be familiar with these and even thinking about careers in this space. You know, for example, right up the top, talking about hardware, a few of my friends work specifically in chip design at IBM. You know, they take years. I can tell you that at any given time, IBM has 3 machines at various stages of what I'll call the pipeline. You know, the Z17 is the current newest model that's out there. There are 2 others already at various stages of design, even though they come out on average, say, around 3 years apart. It takes a very long time to do this right, to do it well, and to account for all that integration that we talk about. You might be aware, if you're not so deep into hardware, the size of today's silicon chips was Z17 runs on 5 nanometer, and we're already making smaller than that. Intel as well is making smaller than that. This size is approaching the size of atoms, which is really, if you think about it, now we have to make transistors on the silicon. Like that's how we create the chip, and some of them will be made to supply memory, and some will be designed to turn into cores that do the processing, but you got to be able to create a transistor. You can't just make a transistor out of a single atom. And an atom is about 0.1 nanometers. So, when we were 40 nanometers, not so many years ago, and we keep going down and down and down, we're running out of runway, essentially is what I'm saying. If you follow PCs, you might notice that the clock speeds haven't increased much in several years. Gets a little bit into the discussion of Moore's law, which technically is still going, but I digress about that. Like, we've got billions of transistors on a Z17 chip. But suffice to say that these easy gains with doubling clock speed are behind us. We need to be more creative to grow capacity and performance, and chip design is just one ways to do that, one of the areas you could go into. But consider as well on here all the programming opportunities. I'm sure many of you program in one or more language. AI is obviously a very interesting variable, a lot of discussion in that space. It's unclear to me if it can reliably take over these massively critical roles. I've heard both extremes that it can do everything. I've heard other naysayers that say, there's no way. I think it's probably going to end up somewhere in the beginning because it's undoubtedly like already a helpful assistant, at least, to get you started and things, and then you can fix it accordingly. Subsystems listed on here. These are deep specialty areas unto themselves. IMS was first created in the 60s to enable the first moon landing. That's what it was for, and it worked. And nobody died. We landed. Today, IMS remains the fastest and most scalable transaction processing system in the world, although I'm sure some of the KICS folks at Hurdley might challenge that. Some of the Brazilian banks are doing 20, 30, 40,000 transactions a second. It's just staggering what these subsystems can do. A retired colleague of mine spent his entire 40-year career in DB2. That was entirely what he did. Very, very specialized fellow, very successful. And when I would talk about the overall system, because to me, well, DB2 is a couple of address spaces. He would say DB2 is the system. In any case, lots of areas and opportunities, and even these subsets could be a world unto itself, providing endless growth, rewarding careers for many of you for years to come. But I want to talk about another path, as you probably know, if you dare, performance analysis, which is my chosen profession. Now, we talk about all these different roles. We sometimes refer to people in these jobs as personas. So one of the questions you could ask yourself is, well, what persona are you? Are you, for example, curious about why? Why is a big word. Why is this application slow or inconsistent? And that doesn't even have to be an application. Maybe you're just, out in the world, and why is this traffic slow? Why is this train slow? Why is this website slow? Do you fancy yourself more of a generalist than a specialist? Excuse me. Thinking about the previous list, again, you could make quite a successful career specializing solely in IMS or DB2, for example. But maybe you're someone that says, well, I want to know a little bit about that, but I also want to know a little bit how it interacts with the operating system and how ZOS interacts with that silicon, those chips you were talking about. What limitations do we have there? How can we optimize these pieces to work better together? So if so, this might be the right path for you. We're going to talk more about it, but the performance analyst role can be summed up into two objectives. We maximize application performance while minimizing resource consumption. Simple, right? How hard can it possibly be? So just a bit more context here. I love dogs. I've got 2 dogs. As we've already said, the mainframe is unique compared to other computing systems. The Z Performance Analyst shares many principles with non-Z professionals, but there's also differences. And just note some of these differences here. Standard solutions in the non-Z space may not be as effective in mainframe environments. That first bullet that I mentioned, the mainframe is a large shared ecosystem. I bolded shared on purpose because that's the key part. Again, I know that Netflix, for example, we once hosted the CIO of Netflix at a conference many years ago, and he talked about knowing the incredible dynamic nature with which they acquire and reduce virtual capacity in the cloud as people are watching TV at night. What they're doing is just simply adding servers, thousands and thousands of servers to meet the demand. And, if you're talking about adding mainframes, when transactions get busy or even turning on cores, you can certainly do that. We call capacity on demand. There's more cores in a machine than a client's originally paid for. So you can certainly turn on more. But that's costly. It's not like, adding another motorcycle to the road. It's like adding another high-speed train. So while you can do that, it's not necessarily as effective or as practical. And again, that the part of the role, the performance analyst, you need to know a little bit about everything, this interaction. When you talk about this interaction among these other applications, in this case, your application that could be slow, there might be nothing to be done with your application or nothing to be done with the hardware. It could be that other applications are suddenly interfering with you in this shared space. So this is back to that needing to know a little bit about everything. It's one of the reasons why it helps to be a generalist in this space. Now, just another risk, I guess, if we choose to call it that in this role, it can be difficult to quantify. So one of my earliest mentors used to say, we're at our best when we're invisible, when the systems are running along, efficiently processing thousands of transactions per second, hundreds of thousands of batch jobs a day, while we quietly study our charts and graphs. We live in an age where economic considerations measure value against tangible, measurable results. How do you measure the value of something that didn't happen? You did a good job. You configure things well. Things are quiet. I experienced this my early career as an analyst at a large bank here in Canada. I use this term efficiency police, but the company brought in this company to kind of analyze what everyone was doing in the different departments in the data center, and they went around and and they had kind of a checklist of standard actions, things like listing on here. How many lines of code do you write today, or what product are you working on? What's the value of that product? When they got to our group, they didn't really have anything on the list. They couldn't really understand what we produced, because they say, you guys are just sitting there looking at charts and monitors all day. Maybe we don't need you guys. Maybe you're not actually delivering any value to the company. Now, we were fine. But I can tell you that in the industry that there is still some of that perception. And I'll talk a little bit more about that. That can be difficult, particularly in the Z age. Think about in a real life scenario, if your mechanic tells you that for your car, if you switch to premium fuel, it will improve the efficiency of your car. You'll be able to drive further on the same amount of fuel. Now, you might agree in principle and say, yeah, I'm sure you're probably right that premium gas is better, but you still might not switch unless you can actually measure the savings. Well, how much am I going to save? How much further can I go? And it can be very difficult to quantify that value. So I like this contrast because it represents in this case, Superman and the wise old man here on the page, they represent two of the most common performance analyst personas. It's a couple of the hats that we commonly wear. So what's Superman do? Well, he provides this real-time responsiveness. This is probably something you hear about more often, and we even talk about this frequently in the context of AI, where we want to automatically detect things and automatically quickly solve them at Superman speed. So yes, while things are happening, bad things are happening, fires are starting, he's zipping around and putting them out so quick that there's not really a lot of pain. Nobody really notices. So he quickly discerns the source of the slowdown or the outage using various tools and techniques and puts that fire out quickly. This is what I call a tactical role. In contrast, the wise old man on the right, he represents the more detailed, longer term approach. He's focused on analysis, planning, and architecture design. He uses some of the same, but also some different tools and data to inform his decisions about what is the optimal configuration. You can't guarantee that things won't break. Things break, it happens. Cars break down. But you can reduce the probability of fires occurring. And this is what I call a strategic role. Now, I can tell you in practical sense, having wore both these hats many, many times, the first one's more visible. You swoop into the operations room when there's a major problem, and you figure out what it is, and you restore service. You're a hero for the day. Management thinks, wow, yeah, you're amazing. Okay, that's great. The second one is actually better for the business, but it refers back to that point on the previous slide. You can't always prove that an impacting event would have occurred if not for your proactive actions. This is that scenario as I described, where the systems are humming along quietly and you're sitting there looking at your charts, and the efficiency police say, we don't really see you doing anything. Superman's very visible. Like, well, we know we like that guy. He's putting out fires. What about the guy that, his quiet actions made there not be any fires for the last year? That's actually better to not have the outage. Now, this can be particularly difficult because what I call the Z double-edged sword. So if the mainframe is a car, you could neglect regular maintenance, not even changing the oil, for say 10 years, and it very likely still run because it's such a resilient platform. But that doesn't mean it's a good idea. And if you operate your mainframe in this manner, you shouldn't be surprised that app performance is inconsistent, costs are high. Now, today's environment, if you're thinking about going into it, I can tell you it's quite fertile for the Superman persona. If you're leaning towards, say, a contracting role, once you learn a few fundamentals, you fly around for a few years, growing and learning your craft, and many data centers will pay you well to be their personal superhero. I try not to put on those tights so much anymore. No one needs to see that anyway. I'm really more content in the old man role for the rest of my career. Okay. Let's get into some details about performance analysis and life skills. So let's just look at a few useful skills for this role, but also practical in life. Right off the top, communication and judgment. You might think with most of these technical roles, well, right out of the way, I don't know how to program, or I got to know a little bit about silicon chips. No. First thing is absolutely communication. Understanding a little bit about priorities. They should not all be the same. If you ask an application owner, is your application important? What are they going to say? They're going to say yes. But if you feed all of their wishes, then everybody's number one. We'll talk about that. That doesn't work. And just a little bit of the back of the envelope math. Queuing theory, not full, just the concept. I'm not a mathematician. A little bit about utilization, capacity, response time, averages, and distribution. And notice at the end here, I've got this Z mainframe fundamentals. So that's not actually the first thing you need to learn. I was a humanities major in university, and I'm pretty good at this. I learned the mainframe later. When I first started at the bank, all I knew about PCs was video games. So, assuming some of you feel like you either want to fly around like Superman or grow gray hair, let's talk about how you can get started. So, as I mentioned, communication is everything. Executives spend millions of dollars, pounds, euros on this mainframe platform, and they're responsible to justify those costs. This unique machine with its vast capabilities is not cheap. So the executives might use words like deliverable, margin, KPI, ROI, whereas us techie nerds, we might use terms like dispatch time and hit ratio. Both personas might refer to utilization as a term, but they might have different interpretations of what it means. We'll talk specifically about that one. So your job as an interpreter is to try and avoid all the technical jargon and just speak the language of your audience. This role also includes judge. Got to be a judge. What does that mean? So it's easier to give an example. My colleague Jerry, I hope he gets to listen to this someday. He does the same job as me. We've been doing it for the same amount of time, longer than most of you have been around probably. And he came up with this example that I'm sharing here. So we've got two scenarios, basically describing conversations between, say, you as the performance analyst and your application teams. And the blue is you and the green is the app owner. So, you might notice, for example, as you're looking at all your various charts and graphs and reports, you might observe, hey, there's a new application here in the system that wasn't here before. So you call or email or send a Slack message or something like that to the application team, say, hey, I see you introduced a new application into the system. And perhaps you get no reply. People are busy. That's okay. No judgment. You might follow up again the next day or the next week and say, hey, could you tell me a little bit more about what your application brings to the company? It just needs to run efficiently. Okay. Much information you get. So the other scenario, say the application owner might call you, perhaps even in a panic. I need my application to run faster. Okay. Can you tell me a little more about your application? I need my application to run faster. Okay. Can you tell me what your application brings to the company? But I guess where this is going, right? I need my application to run faster. Again, no judgment against the application teams. You need to be the judge. They are responsible for their application. That is the center of their world. Again, if you ask them what's important, they're going to say, of course they're important, and they all are. But the big difference in a mainframe environment as compared to, say, a commodity server where you would have typically a group of servers dedicated to each application, in this large shared environment, everyone is relative. Not everyone is number one. Not everyone should be number one. You could set them to do that, but the system would not run well. So maybe in the left scenario, you might decide, okay, we're just going to put this application in a lower performing service class, or we'll continue to try and find out more information. Possibly on the right, we might put the application into an unjustified service class. Maybe, okay, need to run faster, maybe we'll give you a break. But if you do that too much, you're asking for trouble. It's really a good idea to try and find out more. Ultimately, I can tell you in a case like this is an executive level decision and not the individual application owners. You need to get to an executive level that's responsible for all of the applications, where they can sit the application people down together in the same room and say, Tell me why your application is more important than her application. Justify to me why your application should receive, say, 30% of the resources that we spent in this platform. And they can quantify that against, well, what's 30% of their costs, which would be substantial. Now, it's entirely possible that the application might be responsible for 30% or more of the company's revenue. And in that case, that would be a perfectly valid business decision. But in many cases, that's not the case. And these are the areas where you want to try and align those values. So as I kind of alluded a little bit to this one, the app is going to say, well, my app's important. Well, of course, everyone's important. If everyone's important, no one's important. Recall our description of that core AI workload manager. The more you manually interfere with its operation, the less efficient your system's going to become. You want to resist the urge to micromanage. Remember, this is a shared ecosystem. You want to try and understand the root cause of delays, not just react and say, okay, we'll just increase your priority. We'll just increase your priority. Because pretty soon your policy has everybody at number one. I look at a lot of these policies as part of my job, and they're like, I don't understand why this is running poorly. Well, this is why. Because you've asked the system to do something which really can't be effectively done. You've asked it to dispatch everything all at the same time at the highest priority. Unless you have unlimited capacity, which most people don't have because it's a lot of money, you shouldn't do that. So really, the more you play Superman, even though sometimes you have to do that, you got to put the fires out, the more you're going to interfere with that graybeard's design. And remember, think about it. Both of these personas are you. The more you play the one persona, the more you're going to thwart your design. So you want to be strategic. And just thinking of priority, when does priority matter anyway? Well, it matters when there's a queue. Of course, speaking to folks from the UK, you have a reputation of queuing exceptionally well. When there is no queue, priority is really irrelevant. So let's jump in a little bit, queuing and yeah, math and life. Hopefully a couple of these things are also useful. So, as humans, we all inherently hate to wait in general, whether it's sitting in traffic or standing in line. My wife has a Mac. For years, she calls that little colorful ball there, she calls that the beach ball of death. And she'll occasionally call me when she gets that beach ball of death and say, hey, performance guy, what the heck? What's wrong with this machine? I'll usually very sweetly say something like, never trust a computer you can lift. It's not terribly helpful to her. But eventually, things do get done. So you got to know a little bit about queuing theory. And again, I'm not a mathematician, but it's a concept more of anything. And the concepts are really quite straightforward. I like to call it just the mathematical study of waiting. And then the business implications are simple. If the resources are too low, you're going to have long queues. If resources are more than required, you're going to spend too much money. Imagine if you own a grocery store, and let's assume we don't have self-checkout right now. So every checkout that's open, you have to pay somebody. You could have 2 checkouts open, or you could have 20. You have to pay all those people. So you got to decide how many do you want to open? How many people do you want to pay? If you have, if you open too many, sure, there's no lineups, but your costs are going to be high. You might not be able to actually turn a profit in your grocery store. If you don't open enough, the lineups are so long, people are going to leave the store. So it's really just about finding that balance. These concepts are exactly the same thing you do in this role in performance analysis and mainframe. Now, no discussion of queuing theory is appropriate without mentioning the late John Little. He was with us just until a couple of years ago. He was still teaching at MIT. Not even a mathematician by trade, and he didn't invent this theory, but he proved it. It had been used, going all the way back to the 50s by lots of capacity planning type people. But he proved it. He took a summer, and one of his students said, "Hey, could you prove this? Could you prove that it's always true?" And And he did. He got a bunch of books and went through it and then wrote this paper, a proof of the queuing theory was the paper. It was submitted, I believe it was 1962, something like that. And then, the main line there is at the bottom, under steady state conditions, the average number of items in a queuing system equals the average rate at which items arrive multiplied by the average time that an item spends in the system. That's it. It's really that simple. And what's amazing is it is always true on average. Of course, bear in mind we're talking about averages here. But rather than get bogged down in the theory, let's just look at a couple of real world examples here. So again, I'm no mathematician, but I kind of follow the logic. If I've got this equation, which is the people in the system are equal to the number of people, the rate of people joining the line, multiplied by how long are they there. Well, I can switch around the order with an equation, right? So, the first one is measuring what we call occupancy, number of people in the system. Switching it around, if I wanted to calculate, for example, the rate of people joining the line, if I have two things, I can calculate the third thing, right? So if I have the number of people in the system and how long they're there, I can calculate that rate of people joining, which I'll call my arrival rate. But probably most practical is the third way of switching it around, which is how long will I be here? Which is the time in the system. In my case, how long am I going to be here? Whether it's a doctor's office or a traffic jam. And that is simply the number of people in the system, which is that occupancy, divided by the rate of people joining the line, the arrival rate. Well, if you want to play along, we can play a little game. Let's say you're actually sitting in traffic. Let's say this is you. This probably happened to some of us at one time or another. And I've got nothing better to do because I'm not moving. And maybe you get a call in your car as you're sitting there doing nothing, frustrated. And your boss says, when are you going to be here? How long? Of course, the literal answer is you don't know. And the universal answer in my role, I can tell you, is almost always it depends, which as an aside is one of the reasons why I don't think AI can be able to do what we do yet, because it doesn't like that. He wants to give an answer, and the answer is often it depends. But in any case, he wants an estimate. Well, since you've got nothing to do, you could draw on Little's law here, and you say, all right, well, let's start with my occupancy. How many cars are in this system? And since I'm not moving, I can just kind of look ahead to see the view ahead of me here through the windshield. And I'm going to say, let's say for fun's sake, they're about 6 lanes wide. And from where I am at the back up to the next exit, let's say there's 20. I don't know if that's the exact, say about 6 by 20. So I'm going to say there's an occupancy here of 120 cars. Okay. What about arrival rate? Well, I'm sitting again, not on moving on the highway. I look to my right, I see the ramp. Many places they have, you notice the stoplights there. You might have seen those in some motorways where they're just limiting the number of cars that can join the system in order to try and manage congestion. So let's say, for argument's sake, that light turns green every 10 seconds. To let another car in. But you can see there's 2 lanes, so it's going to let 2 cars in every 10 seconds. So if 2 cars in are coming every 10 seconds, that gives me an arrival rate of 12 cars per minute. Okay, so I have 2 pieces of information. We know the occupancy. The occupancy is 120 cars. We know the arrival rate is 12 cars per minute. And we want to know that time in the system, which is how long am I going to be here? "10 minutes. It's an estimate. It's an average, but based on the 2 pieces of information that we have. You could say that to your boss on the phone. You could say, I think I'll be about 10 minutes until I get to the exit. It's something. And hey, you're not moving anyway. You do the same thing when you're sitting in the doctor's office. How many people are coming in? how long are they here for, and so on. One last little angle here. Are 3 lines better? I like to call the one on the left the fast food chaos line versus the bank line. The chaos line, human intuition, we do this when there's a mass of lines that go wide. We'll kind of jump left and right and say, oh, okay, that one looks like it's moving better. I'm going to go over there. Or that one looks like it's shorter, so I'm going to go over there. So we'll tend to prefer that. I'll just pause for a second in case anybody wants to guess, but okay, that's a second. That's long enough. The right is actually generally going to be faster. And why is that? The right, we have like a single queue going into multiple servers. So it appears longer because I have 1 line instead of 3. But one of the big differences between the two, if you take the line on the left, if you're in, that top line, for example, of the 3, and let's just assume they all have a relatively equal number of people, and that line breaks, and by the line, I mean, the server at the front of that line breaks, the machine breaks, or someone's got to switch shifts. You get to the front and suddenly, oh, sorry, shift change, and they got to take the cash drawer out, and you're not moving. And here you just jumped over there thinking it was a shorter line, and suddenly you're stuck while the other 2 lines move. That's very, very frustrating. On the right, as long as at least one of the 3 servers is still operating, the line never stops. Might move slower, but it will never stop. And it's also democratic. The line on the right is what we call FIFO, first in, first out, which means, the next person in line will always be the next person served. Whereas on the left, you can jump left and right. You might win, you might lose. One might suddenly change speed, and that's not, as I say, democratic. Look at it that way. Let's talk a little bit about utilization. We take road trips. This can be driving to work every day or driving to grandma's house, and we take the same route every time. It's the same destination. No one has moved. Your house is in the same place, grandma's house is in the same place, or your work is in the same place. It doesn't change. So why is it on some days it takes longer? Why is that? Again, you're asking, if you're curious, you're asking that question. Why? Someone once joked to me, well, what if I live in a motorhome and it moves? Okay, fair. That's different. We're assuming that 2 locations don't move. Well, you can have a number of measurements listed here. You can have, just a single average speed, which is just, calculated how long did it take you, average speed. But really, if you think about it, or average fuel consumption, you want to break down the pieces to do this. You want to say, okay, of the, say, hour that it took me to drive to my destination, how long was I on this stretch of road where I was going faster, highway? How long was I in this stretch of road where I was going slower? How long was I sitting at stoplights? And compare these pieces is what we call the distribution of that total time. And this is the method that you use as a performance analyst. Something is longer, whether it's transaction or my batch job ran too long. What happened? Well, you're going to start breaking down the pieces. Where did it spend its time? And compare that distribution to the normal shorter run. Say, well, what was different? Was it one piece? Well, there's one section of road where there was construction this week, and that wasn't there before, and I spent a whole much more time there, even though the other pieces were the same. Or maybe it's split. Maybe there's a little bit more in every space, and that might be an indicator of something different. And when we think about understanding that, we often will talk about utilization. So I first Googled this a while ago, actually, to say, well, what is utilization, or what is busy? The boss will say, how busy are we today? And that was quite interesting, that these are the first things I come up with through Wikipedia and these sources are their economic things. When I think about utilization, of course, I'm a computer guy, I'm thinking about processor utilization primarily, or maybe space utilization, things like that. But this is all about talking about asset performance measured, business success determined. Maybe this is why the boss would say we need to run at 100%, which is really not a good idea. So CPU utilization, if I Google that instead of straight, well, then I get a little bit better definition that makes sense to me. Computers' usage of processing resources, the amount of work handled by a CPU. Okay, I can understand that. But you want to consider three variables here: average across time, logical, physical, and average across components. So our average across time, this is Jonopedia. It's very reliable, trust me. CPU utilization is nothing more than a measure of usage over time. The bulb on the left has a utilization of 0. The bulb on the right has a utilization of 100. It's on. If you were to say, what is the collective utilization of those two bulbs together as a single entity? You might say, well, on average, I suppose 50%. That'd be accurate. But what you really got to consider is the time component. Over what time? Am I talking about, seconds in a day, hours in a day? How long was something on? So 80% busy, for example, simply means 100% busy for 80% of the time. If the light was on for 80% of the hours in a day, you might call that 80% busy. The other 20% of the time, it was simply off. The logical versus physical. On the left, I've got a ZOS chart looking at a couple of metrics, MVS busy and LPAR busy. These are logical and physical representations of the processor. Very different numbers. Some cases they overlap. Some cases they're the same. Others they don't. On the right, this the task manager from my laptop, and it's got a single socket, but it's got 12 cores. It's got 14 logical processors. What am I measuring when I talk about that utilization? There's not usually a single number for quote how busy we are. Back to it, that it depends answer. And then the average across components. You consider, say, one machine that's got a single CPU to dispatch for 900 seconds in a 900 second RMF interval. So just like that light bulb that's on for 24 hours of the day, it's 100% busy. And the other one is on for half the day, so it's 50% busy. Whereas another machine, you've got both these CPUs or light bulbs, each on for 675 seconds out of 900. In this case, 3/4 of the time of day. So each CPU is 75%. Well, if someone says how busy is the machine, in both cases, the average of these two machines is 75%. Will performance be equal? The answer is it depends. Capacity. Just a couple of points on that compared to utilization. So the size of the parking lot, in this case, is your capacity. A larger parking lot can obviously absorb more load. A 10 space lot versus a 10,000 space lot. In this case, this example, a 10 space lot with 5 spots full versus a 10,000 space lot with 5,000 full, they're both 50% utilized. But obviously the larger lot has more capacity, so you don't just want to consider utilization. You're going to have very different experiences when you have 5,000 free spaces versus 5. This is what I call bending Little's law a little bit. So if the occupancy space is not unlimited, which is an example of a parking lot, Little's law assumes you can, queue forever. If it's not unlimited, then that occupancy expressed as a percentage is your utilization. Again, 50% full, 5 spots free, 5,000 spots free. It's half of the spots. And if you think about the mall parking lot at Christmas and things are busy, the rate the cars are entering the parking lot is increased. The number of spots is fixed. So the length of time to get in and out will increase even though you're driving at the same speed when you can drive. There's no one in your way. Similar comparative example, increasing from 50 to 60% busy here in this first example. So I've got 500 spots free. And if I increase by 10%, now I've got 400 spots free. Actually, it should be 550. My math's off. But still, in either case, your chances here are going to be quite good. There's still lots of spots free, even though I have a 10% gap in the utilization. But consider from 89 to 99%. So at 89%, I've got 110 spots free. At 99, I've only got 10. Both increased by 10%. both situations here had a utilization increase in 10%. But the total response times are going to be dramatically different. And this is where we contrast what we call response time versus service time. The overall response time is the total amount of time. Just like when we were talking about traffic, how long does it take me to get there? 10 minutes to go to the next exit. Think back to that scenario. Now, if there was no one in your way, it does not take you 10 minutes. You remember the picture. It wouldn't take you 10 minutes to drive up to that sign. It would take you seconds. You hit the gas, there's nobody there. So just like you see in the chart here, the queue time, which is the waiting time, is almost always the larger portion. Your service time is how fast you can drive, whether it's just pulling into a spot or driving up to that exit. That's fairly fixed. When there's nobody in your way, you can go the same amount of speed every time when you're not impeded. So that should be quick and consistent. Mainframes, when we talk about this 100%, sometimes people say, oh, well, a mainframe can run at 100%, and it's happy. Well, yes, mainframes generally do run better than other platforms at high utilization, but you should still avoid these extremes. This queue, as you can see here, you're getting up over 90% plus. Just look at that queue time, that wait time. So even though your response time, the light blue at the bottom, you can see it's 1 in this case. Well, 1 second, 1 millisecond, whatever units you're using, it doesn't change. But your wait time goes off the charts. So, the service experience by the application is quite excessive. This is why these excessively high utilizations are inefficient in any platform. Okay, last, we're getting up we're at the top of the hour. Yeah, so last part. Short, Z fundamentals, excuse me. I'm Canadian and I find myself saying Z all the time, but I spend a lot of time in the US. One of my IBM colleagues likes to refer to people like me as mechanics. So we know all the parts in the example here on the left. We know what they all do. We know how to put them together. We know how they interact and at a level of detail that's not typical. What I would say, if you're looking at this role, you don't need to necessarily know it all at that level, but you still need to know how to drive. You need to know, for example, if you just see an engine light come on, but there's no other abnormal symptoms, you're driving, for example, the engine sound didn't change, didn't hear any loud or erratic noises, it feels smooth, just the engine light came on. In that case, you might just say, well, I'm going to make a mental note to see my mechanic next week. Versus you see an oil pressure light comes on. And it's flashing red and the engine starts smoking. Well, clearly that means you should stop right now. That's not the same as make a note and talk about it later. Software and technology has improved and continues to improve dramatically. So it's likely that we won't need as many mechanics, using air quotes, in the future. But we need drivers. I can tell you a lot of the client situations that I get pulled into in mainframe sites. Very often the problem is not some archaic needle in the haystack that I had to draw on every trick I know to figure out. It's very often these fundamentals that I've talked about, the utilization, priorities, balance. Very often that's what it is. It's fundamentals. And it's because they don't have anyone that knows how to drive. For good or ill, perhaps back to that said double-edged sword, they said, this machine is so resilient, it just keeps running. We don't need performance teams. We don't need people because it's just fine. But then, bad things happen and they don't understand why. And, when you're discussing with them, to use that car analogy, you look at some of the reports and say, well, when's the last time you changed your oil on this car? And they're like, what's oil? Okay, let's start there. Because that's going to make a big difference. And I can tell you, just knowing these fundamentals can take you a long way today. Although, if you're truly ambitious, IBM will always need a few mechanics if you really want to go all the way. I'm going to retire. um, there's a few colleagues that I know. A couple of sources here, just as wrapping up. If you're not familiar with Redbooks are fantastic. Great place to start. These books, if you're not familiar, their aim is to bridge this area between, say, a high-level concept and detailed reference manual. I still love and reference many of them. I had the privilege of co-authoring on one last year. Some of the best are written by if you haven't heard of the irreplaceable Frank Kine, you might know the UK's own Martin Packer, good friend of mine. It is not too much to say he is arguably one of the best performance analysts in the world, living there in the UK. Martin is what we call a gold author. He co-authored right in the center of the page at the top, that the Z17 technical guide. His name is on there. And he co-authored one of my favorite books that I still reference from 1995, among many others. Some of those old ones can't be found online. So if you're really interested, reach out to me. I maintain a healthy PDF library. I long ago found, looking things online, things that I could find before weren't there anymore. So I started keeping copies. So I've got a lot of these. Okay, wrapping up, I just want to close with a brief story. You see the roles, the various hats. If you decide to take the leap into this field, these are some of the personas. Some of you might be familiar with this story. It's not new, but I think it tells it well. So once upon a time, there was a company that had a big machine, and this big machine generated enormous revenue for the company. And after many years, the graybeard engineer, we'll call him, he retired, and a few weeks later, the big machine broke down. The manager couldn't get the machine to work again, so the company called in the graybeard as an independent consultant. Graybeard agreed. He walks into the factory. He studies the big machine from various angles, walks around, looking at it, peering through those little glasses of his. Finally, he focuses on one specific spot on the big machine. And he pulls out a hammer and whacks that spot. And the machine suddenly springs to life. So everybody's happy. Graybeard goes home. Company's making money again. The next day, the manager receives a bill from the graybeard for $5,000. Manager is furious at the price because Graybeard was not there that long. He refuses to pay. He demands an itemized invoice. Graybeard agrees that this is a fair request, and he complies. The new itemized bill reads, hammer, $5. Knowing where to hit the machine with the hammer, $4,995. Performance analysts know where to hit the machine. And that is all I had. I've not looked at the chat box. I'm not sure if there are. I should look right now. Friends will hate me when I make them do this as a new car game. Yes. Beach ball of death. Yes. WLM is so cool. Cool. Great. Great comments. Any questions? Okay.
I do not have any questions. I think it was a very informative session, lots of new information, and I'm very glad I attended this, to be honest.
Yeah, well,
So,
thank you.
thank you very much for joining us. We're going to put it on YouTube and maybe send you a link if you want. But we're going to do a post about this much later.
Sure, sounds great.
Thank you very much. Thanks to everyone for joining. The YouTube people, I don't think they're going to have any questions, but yeah.
No worries.
Thank you very much.
Right. Thanks all.
Have a good day, everyone.
Yes, thank you all for coming today.